in another 1 minute, I guess. All right, let's get started then. So hello everyone again. So from today, we're gonna talk a little bit more about machine learning, and especially we're gonna talk about this very popular architecture called attention, and how it's been evolved through today, and kind of what are the potential like inductive bias are introducing this type of architectures, and then in the last we will also mention about some like specific type of attentions that are designed for modeling protein sequences, like in AlphaFold. All right, so I know that some of you might have heard about or are familiar with the concept, so bear with me if I'm talking about something you already know. But if you have particular questions or you think some part that I teach may not be correct, you can feel free to raise your hand and correct me. All right, so yeah, so actually, I think a lot of the momentum that was put into building attention really start from the field of natural language processing. So if we look at the general timeline of attention or transformer, or how it kind of evolved from like pre-attention era to right now, like the biggest driving force of like almost all deep learning in different fields, not just natural language, but also like computer visions and also like, like protein folding and computational biology. It's actually interesting that attention has been introduced earlier than transformers. It was actually the first attention mechanism can trace back to like as early as 2014, where like what's before attention is really the really powerful family of recurrent architectures that we talk about, like I think 3 lectures back, where these recurrent neural networks and especially like LSTMs and GRUs are built to do this machine translation task, which really transformed the field and basically taking over the kind of the neural machine translation field. Up until 2014, there's the first attention mechanism introduced, and it's different from the self-attention that is used in transformer nowadays. But I think people start to form some intuition about how attention can help solving some information bottlenecking issues. And then in around 2017, which finally transformer and self-attention is introduced, which there's this explosion of application transformers in modeling in natural language processing. And around like somewhere in like 2020, transformer also been extended to other fields like vision transformers in computer vision and also like AlphaFold. Basically, this attention concept has been like expanded to a wide range of field where basically it has become the single building block that is very powerful and flexible to deal with all kinds of data. And it's also like the charm of this architecture. And of course, like there are certain types of mechanisms for training transformer, particularly the decoder type of transformer or like decoder only transformer that becomes the language model or basically the large language model we call like today like GPT and Llama. But besides that, there are also other types of like language models. For example, there's mask language model, which does not focusing on next token prediction, And those kind of language model, or like kind of encoder-only language model, is also very powerful in the field of computational biology because of its capability of learning representations. All right, so what happens before attention is introduced, right? So when we talk about the recurrent neural networks, we talk about different frameworks of applying recurrent neural networks. Particularly, there's a task called seek-to-seek, where basically, I think it's more natural to think it under the machine translation realm, where you have like a source sequence, which could be maybe an English sentence, and then you have a target sequence, which could be like, I don't know, Japanese, and you want to do this sequence-to-sequence translation task, which has been the very popular and important task in a natural language. So this seek-to-seek architecture is introduced, which essentially use two recurrent neural networks, where the left-hand part, we can call it encoder, where we apply RNN on top of the source sentence from left to right, or we can use like any kind of like bidirectional LSTM or like GRUs. And then at the end of the source sentence, you will have one of these embedding, usually the last token, the embedding at the last token. We will use that as the encoder or embedding for the entire source sentence, and then pass it through another set of RNN, which is used to directly generate the target sentence from the first token along. And you can see that there is this passing of information from the source sentence to the target sentence through this last bit of embedding. And what it does is really just use it as the additional like state or hidden variable and pass it through as the beginning token of the decoder are your recurrent neural networks, right? So it is really like, although like seems to be like very simple, but it's really powerful, and it's taking over the machine translation field from like Google and the other search engines, which they spend like hundreds of thousands of labors on building like a traditional statistical neural translation models, which are like completely beaten by this simple like seek-to-seek model or neural machine translation model that a few engineers can build by themselves using like a couple of days of training. However, there's still some issue with this seek-to-seek model, especially with this recurrent neural network architectures. Particularly, as we mentioned, like a lot of the information, basically all of the information in the source sequence is being encoded into this single like embedding at the end of the source sentences, and it's passing directly to the beginning of the decoder, which means that throughout the entire decoding phrase, we're not allowed to change this source embedding anymore. And basically, you have this one-time chance of passing the information through this last embedding. And it's not really flexible, and it also produces some information bottleneck, right? Because what you can get is at most the information that's being compressed into this last token, and this information may not be the most important information for every single token prediction in the decoder. It might be important at maybe the beginning of the target sentence or the middle of the sentence, but it's not like it shouldn't be fixed across this decoding process. So how to solve this like bottlenecking problem is one of the motivation of the invention of attention mechanism, even though it's not self-attention yet. And the second limitation of this recurrent neural network is, of course, this kind of linear interaction distance, or the deficiency in propagating long-term interactions between different positions. So for example, because of this recurrent property of recurrent architectures, you have to, information has to be encoded sequentially, so you cannot jump through the last token. You cannot jump through these intermediate steps, because these hidden states needs to be built gradually by doing this recurrent, like updates of the hidden state. So what happens is, for the very long sentence, if you have two token, or for example in the protein case, if you have two like amino acid that are kind of distant in the peptide, in terms of in the residue level, in the index level, they're very distant. But when they fold, they actually interact with each other, right? To capture this kind of long-term interactions, if we're using the recurrent neural network, it will take linearly, like the number of steps that takes to propagate this influence from the first amino acid to the second amino acid is linearly growing with the distance between them. And this can be really bad, not just because of the efficiency, but also because of the vanishing gradients and all that kind of backpropagation stuff. And the other thing is directly impacting the deficiency or the lack of computational efficiency for recurrent neural network is the lack of capability to being parallelized. So we talk about this truncated backpropagation through time, right? So you could chunk your thing to shorter time windows to make the backpropagation more efficient, but that still cannot resolve this sequential dependency. You cannot compute the next block before you compute the first block. So nothing can be parallelized under this realm. However, parallelization is really important because we want to make use of the GPUs, which is really good at doing parallel computation, especially for these matrix matrix multi-take operators. So there has been a strong motivation on trying to figure out a good architecture that can be parallelized during training. So the introduction of attention is really try to solve a lot of these problems, starting from the information bottlenecking to making it more parallelizable and making the information flow without need to traverse the long distance. So the core idea is basically in each step of decoder, we don't just rely on the previous state of the RNN, but instead you could directly connect it to the entire encoder, and you can focus on whatever part that is important for your decoding, for the current decoding step. This will remove the information bottlenecking because you're allowed to visit the the source sequence again at each step of decoding. So you don't need to necessarily rely on the beginning of the decoding step to extract all the necessary information. So a naive solution for this information bottlenecking is perhaps definitely to use all possible information in the source sequence. So we can use this very naive, just the mean pooling. Basically, we take every single embedding in your source sequence, and we just do a mean, a mean or average of them. So we have all the information. We don't necessarily sub-select any of them. However, this is kind of not very informative, and because in the particular part of the sequence might be more interesting than the other part, right? So we can think of attention as basically an adaptation of these mean pooling mechanism where we try to add some weights to this pooling, where we can, based on what is important and what is not important, we can adjust our weights to get a weighted averaging of the information at different tokens. Furthermore, it can be also thinking of in terms of when you do in traditional kind of retrieval tasks, you have this lookup table where if you have some query information, you can try to query that into, if you have a lookup table of the potential pairs to your query, you can basically just to try to look in this lookup table for keys that are the best match of your query, and then just retrieve that value. This is a very simple way of retrieving this information because it is basically the similar mindset when we use attention, except that now instead of doing this hard retrieval of a single lookup, we have this soft retrieval, or this we call soft attention across all of these keys in the lookup table, and we're able to include multiple entries in the lookup table. So basically, the left-hand side is kind of one way of interpreting what this attention is doing. So each of the key and values can be think of as the embedding of each single token in your source sentence, right? And every time you decode something, you could use that decoded token to generate some embedding, which you could use to query the different tokens in your source sequence. And then try to pull out things that are more important based on a certain kind of attention weight multiplication, attention weight computation, and then you just do the weighted sum of these values. Any questions so far?
You said that attention was discovered in 2014, and then the attention as all you need was 2017. What was the impetus for discovering attention? How did it come about? What did they use it for in those 2 years?
Yeah, I think one of them is actually used also in computer vision, where you try to retrieve the important, interesting pixel in the image when you do this image captioning. The other thing is from this seek-to-seek model directly. So just to solve this like bottlenecking issue that we talk about, right? We could basically do a more flexible way of passing information from encoder to decoder, and this is not necessarily transformer because it's not like self-attention yet. So you can think of this as a general form of attention, where you can, like anytime you have a query and you have like a set of information you want to like choose from, you could use attention. And self-attention is just like one particular example of attention. Basically, how you build the value of query and key and value can be different, and I think it's defined as more general in earlier days. So yeah, basically seek-to-seek with attention is as I said, in each step of decoder. But again, this is still using RNN, yet we're not using transformer, overall at that stage yet. So we only use attention as a way to, you can say like cross attention. Basically, you pass information from like one side to the other side, but the building block of these two sides are still kind of recurrent architectures. So what happens is like during your decoding stage, right? Like at each time you decode, you could then look back to the source sequence through this cross attention mechanism, where the embedding from your decoder token is being used as the query, and the embedding of these every token in your source sentence is used as keys, and you can also try to come up with values associated to these keys, and then just do this soft kind of like dot product, which this dot product is used as the attention weight. And then you can do it in different steps. You can see that the weight will change. Like maybe the first step, the first token is more important for the decoding. So you will essentially have like higher attention weights. And you can use this distribution. You can apply a softmax over these dot products, and then you can get this weighted sum of these hidden states. So like, you don't even necessarily have a value here. You can just reuse the like hidden states as both as the key and the value, right? So essentially, in this stage, you don't. I mean, someone can maybe have come up with like a particular design of value, but at this point, you can treat basically value and keys are the same, like they're both embeddings, and we just try to retrieve things that are similar to, in some sense, like similar to the query embedding, and try to do an average, weighted average on them. So then you can basically use the output of these attention with this decoder state, and then use them to decode the token at that place. So this is more, and then you can do it for each single time you decode. You have this opportunity to look back into the encoder, which again like solve this information bottlenecking issue, as mentioned earlier. So you can do this like, again, you still have a recurrent neural networks for the decoder, but the only difference is that at each step you look back to the encoder to retrieve more information. Any questions so far? Cool. Yeah. So basically, in this earlier attention mechanism, we just need to basically decide, like use this hidden states H and of the encoders and the query. Basically, at each time type step T in the decoder, we also have a hidden state S. So we just like the query, and we just directly multiply that with the hidden states of the encoder, like treating them as key at this time, and then we can apply self-attention, softmax over all computed attention scores, and then we do the weighted average on these hidden states again. So exactly like I said, the query and the keys and the hidden states are reused both as the key and the value in this earlier attention mechanism, which could be also like maybe a deficiency of this vanilla attention mechanism. But I think, at the end, we know this like high-level mindset of using attention being like just a way to softmax. And then there's a lot of different way of computing these attentions. Of course, we could compute it with like the dot product, which is the easy way. But you can also try to change this operation of attention score computation to like other things, other types of architectures that you think can like commingle the information from two embeddings. But the general formulation is always this. So basically, like there are different proposals of doing these modifications. For example, this is the most simplest way, just do like dot product. And you can also do some bilinear kind of attention where you also introduce additional weight matrix in between. And basically saying like for these pairs of dimensions, I want to put more weights or more attention to it. And there's also like this kind of low rank multiplication where you could try to factorize this this bilinear like weight matrix in between into like as a low rank operation on your source token, and then a low rank operation on your target token, right? And this looks very familiar to us because you can think of this basically as the earlier form of self-attention, where you try to particularly use some embedding to transform your query, and you can use similar thing to transform and to get a key. So I think this is kind of the earlier form of what will lead to kind of the final composition of self-attention. And also, of course, there's also other types of attention like additive. You don't have to multiply them together if you believe there's some additive information will be important. Any questions? Okay, yeah, and then, so as I said here, it's not really additive because you could definitely add nonlinearity on top of this input. You can just treat the dot product, you replace dot product basically with a more general form of computation between two vectors. And then there are papers also showing that these, sometimes like these MLP operators, aggregation could be more effective than just doing the dot product because dot product only reflects one type of like sine cosine similarity. Questions?
Are there specific applications where one type of attention is more performs better than others?
I think a good question. I think right now mostly the dot product attention has been powerful just because of this embedding in between, like this bilinear transformation. So I believe like this, if you make your U and V powerful enough, it can kind of replicate some of these additive attention or MLP. I think it really is application specific, and again, I don't have an answer for like every single task. Maybe one of them outperform the other, but I think you can basically get some inductive bias when you try to like think about what kind of problem we're dealing with. But this simple dot product with this like U and V transformation has been really powerful and almost like used everywhere in the self-attention.
Yeah, I guess a more specific question would be, has anyone tried to use, any of the, for example, the additive to solve any of the problems and see it to be effective or anything?
Yeah, I mean, there's papers about this. So, I mean, of course, it's, I've definitely seen people using like non-dot product way of combining these vectors. And I think especially like for later on for like positional encodings, which we'll talk about in a bit, you can also choose to like either do additive positional encoding or let the MLP to decide like how you want to combine your positional encoding with your token. And that also been proves to be very effective in protein modeling. So yeah, again, I think, this kind of linear matrix dot modification would be ideal because of the efficiency of using it in GPU. So there's all sorts of constraints here. And I believe if you add more nonlinearity into these embeddings, you would definitely get like more expressive power. So you can get, it's essentially what you get from additive attention as well. Great. So now we look at this attention mechanism, right? It has been only used to do the cross attention, or how, like basically how we change the way we carry over this information from encoder to decoder. However, the encoder and decoder themselves are still doing this kind of expensive, like recurrent architectures. Then we kind of have the thoughts that, like, given that RNN, what RNN is doing is just doing this passing of information to the next state or next token. Like, why use it at all, right? Can we just get rid of RNN and directly use all the attention to do every single information passing? And that kind of motivate this concept of self-attention, right? So instead of doing just cross-attention and having these two kind of isolated blocks of tokens, we kind of just consider everything together as one sequence. And the way we're passing information is basically, especially talking about the next token generation task, which is like the autoregressive generated model. What we need is just every time we decode a step t, we want information before t. So we just can use attention to directly doing this information propagation and completely remove RNNs. So like this is kind of the hypothetical, diagram of like decoding stage if you replacing everything with attention. So basically, we still at the time t, we want to decode this token. Then we can still have this notion of key and query and values. So we can just try to use the similar like soft lookup table thing. But the only way, the only thing we need to solve here is how we define key query and values, right? So previously, we saw that in the earlier stage, we just use embedding directly hidden state as a key query and values. So one step further, we can basically think of a more effective way of transforming these embeddings into key query and values by adding this additional embedding matrix for each of them. So basically, self-attention has modified a few things from the earlier cross-attentions. The first is like every single token in the previous region of your sequence has been treated as the tokens that you will attend to. There's no separation of encoder-decoder blocks. And you will use the embedding from each single token as the input to 3 separate matrices, which are the K, Q, and V, where each of them will transform your original embedding into a vector of keys and query and values. So instead of directly using the embedding, we do additional transformation, and this transformation is different between key, query, and values. And so we're not reusing them, just the X, and we have Q, K, and V here, which are learnable from adding this additional variability to the attention. And then still, we need this softmax to kind of get a normalized score because we want to do the weighted average, and it will be if we normalize it, everything is kind of between the range of 0 and 1, and we have this cool notion of like taking the expectation of the key and queries. And finally, we just need to do this weight. After we compute the weight, we can do this softmax, with weighted sum to get the value. And I mean, this is very straightforward, but there are also some downside when we move from recurrent neural network to transformer, right? One apparent issue is this invariance to the ordering of tokens. So if we just directly take a weighted sum, it's essentially like kind of a set operator that does not have the notion of order. If you swap tokens in the sequence, you get exactly same output, which is not ideal if you really care about ordering. Of course, there are certain cases you may not care about it at all. I mean, but in terms of you think of protein sequences, the ordering still matters, right? Because first of all, we have this like N-terminal and C-terminal, as I said, like our sequence definitely has order. And the positioning of, like the relative positioning of the amino acid also matters. Like the distance of the amino acid and where they are in the sequence definitely matters. So how can we inject some information such that we can tell the difference between different positions and still able to use the attention mechanism? A straightforward solution is I just change the input a little bit and I change it differently. Like if you're in a different position, I make sure that I have a unique and different operation that I apply to each position, and it's only depend on the index of your operation. And then there comes this what we call positional encoding. What we need from this positional encoding is like we want to apply this positional encoding and make it unique for each different dimension of our data, and we also want it to be unique across different index in the sequence. So a very smart idea is to make use of these sinusoidal position representations where you use the sines and cosines and kind of divided it by the number of dimensions and the number of index in our sequence. We can get a really unique operation to our input token. And this is kind of good because it kind of has this different periodicity that including like basically if you have different sets of like hidden dimensions, you can have different periodicity that try to capture like some short like high frequency patterns and low frequency patterns. And you could also like extend it as long as you want. However, this is kind of a fixed encoding. Once you compute it, it's kind of already there. It gives you this very strong inductive bias, which may not be ideal. So if we were to do everything end to end with machine learning, and you can definitely like make this part of the model also learnable. So then there's this learnable position representations where you, instead of adding this fixed sine cosine value, you can apply a transformation on top of that, or just make up some function, which would define some function, which is the function of the index, and directly learn that during this attention. Of course, this is giving you the flexibility, so you kind of learn how to fit the data well. But there could be also some downside because you fit the data too well. You're not able to extrapolate meaningfully when you have like longer sequences or you have out of distribution sequences. And there are more when we look into these positional encodings, actually there are different ways of designing it, such that they also reflect some inductive bias that we want. Particularly what we call this type of embedding, we can call it kind of definite positional encoding. However, especially for example, if you think about protein, right? It really doesn't matter if you are if you're interacting, like the two amino acid are like forming a loop, right? They're contacting. It really doesn't matter if this loop is in like from the 3rd to the 10th residue of your peptide, or it's from like 103 to 110. So like similar local physics can make similar contact if the kind of a local like relative distance is the same, right? So we kind of have this a little bit like you could call it a translational invariance of like this if two things are relatively the same, when you have this translation across the index, you could like expect some similar local effect. So the relative position is basically one way of thinking about the particular bias that we can introduce to our model. So there's this relative positional encoding mechanism, which instead of having this absolute encoding, which computed only based on the indexed, we can also compute it, try to apply some operation to our attention, such that the attention is differently computed, but the difference is determined by the relative distance between the two tokens. So the earlier types of relative positional encoding use this kind of, like a linear hard encoding. Basically, what you do is for each pair of key and query dot product, you try to add this positional information into the, this should be the key value itself. And then when you do this softmax, you again add the additional bias to the softmax, the dot product attention. So effectively, you have these two additional weight biases, which are pairwise biases, which only varies depending on the source and the target location of these tokens. So essentially, what it does, you can think of it as like for every pair of token, right? You do this attention, which is the dot product of between key and query, right? And we just want to make some operation to change the key and query and this dot product itself, such that this change is only depending on the distance between the two. So basically, at the end, you could also, the problem becomes learning this additional like modification to repairs of key and queries, and you can also clip this this bias that you're adding into by like saying that like beyond this distance, I don't care anymore, like if they're any longer, if the distance is any longer or not. So this is very powerful, but like doing this addition is very expensive because we need to do this addition before and after the dot product and within the softmax, which makes it not very efficient for GPUs. And also, like, geometrically, it's not very easy to make sense of, I think. But again, it's definitely useful and proved to be effective in some of these neural machine translation tasks. But what I want to highlight more is the later invention of these rotary positional embeddings, right? So instead of doing the addition, why not do multiplication, right? Multiplication is much simpler. We can represent it with matrix multiplication, and we can compute it very efficiently with GPUs. So the simple ideas come from like this rotation matrix, where you can basically try to rotate the, so we can consider each of the embeddings at each token as like a vector, right? This is a two-dimensional visualization, but you can imagine higher dimensional visualization. So what if I just rotate these vectors based on the distance between these vectors, between this token and the previous token? So the kind of the idea here is like we want to rotate this token, but the angle that we rotate is depending on the distance between the two tokens. Like the longer they are, we want to kind of rotate with a larger angle. The good thing about this is you can see that if this rotation is computed, if the angle is only determined by the relative distance between the two tokens, right? No matter where they are in the sequence, right? As long as you have the direction of one token and the other token, the kind of the translation the rotation you applied it is always the same. Even though the embedding themselves can be different because like there are different positions in the transformer, in the attention, and the way you compute attention will result in the different embeddings. But the rotation operator we apply to the two vector is still the same. So the dot product between these two will go through similar type of rotation. This is kind of visual concept clear? Great. Right, so now we can look at inside the math behind this. It's really simple. Like we know that we basically want some multiplicative operations to our attention. So we can apply this to our key, again, to our key and to our queries. And then in this soft attention, which is kind of the dot product of the two, these two multiplicative part will, you can multiply them together, then you will get this difference between m and n, which is only depending on the difference of m minus n. And we can represent this with the complex number, and there is this. We can use these Euler formulas to write it down into the matrix form, where basically we have these transition matrix, which is the original weight we apply to our key or our queries. So this Q and K here just means that this can be applied to either key or query. So it's the same kind of in similar transformation. And this is our original input, where you have two dimensions, and then you can have xm1, xm2. And for this particular input, we can apply the two sets of transformations using cosine and sine. And these two, if you visualize them in 2D space, will exactly rotate these two-dimensional vectors with the angle of m times theta. So effectively what we're doing is we try to divide our, suppose we have like a d-dimensional embeddings, right? We will divide it into two parts. And to compute this matrix, we basically need to have like for every single x, we need to have these operations. If we compute it as like a big matrix, you can see that only the diagonal part will get this non-zero sine and cosine value. So we're doing a gigantic matrix multiplication with a lot of zeros in off-diagonal region, which is not really effective. So why not doing it more efficiently? So if we kind of try to do a decomposition of these operation, we can actually like really simply decompose it into just an operations on the x, which with the cosine, and the operations on the x with some sine. And we can compute this very efficiently, right, with like this product, the Cartesian product. And I think, so effectively you just need to divide your, your embedding into two parts with two of with sum of like every other dimension of them have a flipped sign, and then you can do this cosine and sine multiplication to this two part of your x, and then add them together, and that will give you the right rotation without needing to do this gigantic matrix multiplication. So yeah, I think visually this is try to show what apply to the actual like embeddings. So these you can think of these with like as the embedding of that token at the first sentence, right? And so you basically have divided the things into x1, x2, x3, x4. So every two like dimensions in your D dimension is paired up, and then you can do this multiplication with this matrix, right? So you will get cosine m theta 1 minus sine m theta 1 for x1, x2, and then you can have these cosine m theta 1 plus sine m theta 1 between x2 and x1, and that is effectively doing this like multiplication that's shown here. So for every pairs of the embeddings in this D-dimensional embeddings, you can do this multiplication, and effectively your key and query vectors now becomes this thing, which is kind of being rotated a little bit. So every positions has got their own like different rotations. You can see the color of different position, which represent how much they're rotated. And when you do dot product between the pair of them, right, you can get the difference between these two angle, which determines like effectively the rotation that's applied to this pair of attention in your final attention matrix. So if you visualize this attention matrix, it will be looking like something like this, right? So it's basically only like the off-diagonal region, you have this radius of radius shade patterns, which only like for everything that has the same relative distance will get the same transformation in this rotation, in this attention matrix. This is very, very powerful. Like you can see that, for example, in the Llama 1 architecture, they actually use this rotary positional embeddings. And I think it really makes sense in protein design as well. Like I said, like the definite location of the amino acid only matters to a certain amount. But the relative distance really matters more because we know the kind of the biophysics that's acting is more like local. And I think out of my personal experience of using like different attentions to our generative model for proteins like protein backbone design or protein sequence design, adding this rotamer rope embedding or rotary positional embedding like drastically improve the efficiency of training, and we can see like the model fitting to the generative distribution much faster if you don't use rope attention. All right, any questions so far? Computational benefit?
So like because of this like matrix multiplication, the computation becomes faster when you use
Yes.
Is there like a benefit in terms of accuracy or like any?
Okay, yeah, I think that's a good question. I think definitely there's a benchmark between definite relative position coding and rotary, and I believe rotary is more powerful. And I think I really like this like rotation visualization. Like we have, considering things are like being vectors in the space, this rotation transformation really makes a lot of sense, like mathematically as well.
So does that allow you to kind of
Yeah, I think if we believe that, I think definitely I think the inductive bias here is closer to what we expect in the word vector space, where we kind of expect that like the relative angle of the vectors give us a lot of information, and that has been visualized in a lot of these earlier natural language, visualization analysis of the word embeddings. So it's like really the angle that matters, or like the kind of the relative, vector change that matters. Cool. So let's get to some additional modification that's added to the attention, right? So if we think about attention, it's really just weighted sum, and it's just linear weighted sum. Even though we have this softmax, right? But if you stack these attention blocks for multiple layers, effectively we're still getting some linear transformation because it's all linear sum, aggregated together. So how we get rid of this? Of course, the simple trick always is to add some linearity. So after every like linear self-attention, what we can do, the really simple thing is just add a position-wise feed-forward neural network. So this is different from the the original like fully connected neural network where you apply this gigantic FFN across all inputs, right? It's not really flexible. It cannot deal with flexible like length. So here we only add this position-wise feed-forward neural networks. So we only operate on a single token space. It's not like you concatenate everything and get this gigantic transformation, right? And then after this nonlinearity, we can like try to look across different positions with attention again. So this will enable us to inject the nonlinearities effectively, and it's enable us to stack multiple layers of self-attentions.
So how are those networks trained? Like those feed-forward blocks?
So I think it's just trained end-to-end together with the entire neural network.
Oh, so what about the different lengths? Like input sequence could be different lengths, and some of the feed-forward networks might not be used directly.
Oh, so that's why I mentioned it's like a position-wise feed-forward. So it doesn't matter like how many token you add because it's only applied to each single position. Oh, I mean it's just the weight is shared across all different tokens. So it's not like you have a independent set of it's sharing the weight is shared. Yeah. But it's applied position-wise instead of like to everything. I think in the actual language model, I think at the end you will still have some notion of like global aggregation of things that where people might use like a gigantic, fully connected neural network. But I think for us, effectively, we mostly use this position-wise transition in the intermediate layers. Okay. Any questions other than that? Cool. And then the other issue, which might be an issue, of course, for one type of transformer, one type of attention is the in the autoregressive setting. If we recall what autoregressive generation is basically you have this Markov chain of like decoding the next token given all the history up to the time step before this token. So this is very useful if we want to do like a fully generative model. And we want to generate from like small number of tokens to a larger number of tokens. So we cannot leap through time and leak information from future. And this is very very often used in like language model, of course, if you care about next token generation. So to stop this, so basically when you decode, we don't want to use the information that will only appear after the token has been encoded, or like call it future information. So simple trick we can add is this kind of causal mask to our attention. And then, of course, this is the first way of using mask in our attention, right? Basically, when we do this dot product, we can decide which of these attention scores we will be using in the final softmax. So for the tokens that appears later than the current positions, we simply just don't use the value from there. And effectively, this is like assigning a super negative value to attention score, or basically, or multiply your attention matrix with 0 for those part. And this can be handled by some efficient architectures that kind of deal with a sparse attention. Sometimes you can also call this like causal mask because of this kind of causality you're introduced into the sequential generation of tokens. But I think what this tells us is really like we don't need to treat attention always as like a fully connected adjacency matrix, which is kind of give you all the information about all pairs. A lot of time, if we know there are certain positions that are like not important, they don't necessarily need to be interacting, we can like drastically adding different types of mask into our attentions to play with like how things are looking to their each other's. And this also have been shown to be very effective in protein modeling as well. I think in the one of the future courses we'll talk about like AlphaFold 3 especially. They also actually use what they call like local attention window. So you actually only look at the 64 adjacent amino acid or 32. I forgot which one this is. Sorry, I need to double check. But you're basically looking in the local area in the sequence in one of their attention unit. So this way you can deliberately introduce this localness into the attention mechanism. Cool. So far we have visited all the kind of the basic building block for a self-attention. So just to recall, we need this attention mechanism where we introduce this key query value and this soft-max attention, and we add mask because of this causality, and we have these positional encodings that deal with order invariance, and we have these nonlinearities to deal with like try to inject more expressibility of our model, and finally we have like flexible masking. Depending on like how much information we want to block. This is almost the same as the transformer, right? So now basing on like all of these building blocks, actually we were able to kind of build this very powerful architecture called transformer with the paper kind of attention is all you need. So you probably see these figures like 1,000 times, but what it does is really like trying to use these attention blocks and try to kind of build an effective seq-to-seq model, where again, like this is still a seq-to-seq model, and it does involve still an encoder part and a decoder part. And so what's different is like within each of these encoder and decoder, we no longer use recurrent architectures, and instead we use the attention architectures that we just talked about. And there's still this a cross attention step between encoder and decoder that transfer the information from your encoder to the decoder. And later on, we also noticed that we don't necessarily need to stay with the seq-to-seq form, because a lot of time, like either we just care about next token generation, or we just care about like try to learn from a given sentence, right? To learn some property of this entire sentence. So that kind of gives us two ways of setting up our transformer neural network to be just the encoder, or we call like BERT architectures, or just the next token predictor, like a generator, which is the kind of GPT framework that is using large language models. So what's inside these encoder and decoders? Of course, we've talked about most of the things here, but still they have a little bit more modification to what we just talked about in this basic attention neural networks. The first thing, of course, the embeddings and rotational, the relative positional encoding, the positional encoding, either relative or definite, is still there. One modification is instead of using a single set of key query values, they use this multiple sets of key query value, what they call multi-headed self-attention. So it's really simple. It's basically, you can consider like duplicate your attention, all the embedding layers associated with your attention into two sets, and they kind of operate simultaneously and independently when you have a sentence. And this is interesting if, like, for example, if you care about different local patterns, or different patterns in the sequence, right? If you want to, for example, have some sets of your part of your network to detect relationship with like entities. So assuming we're like learning embedding from the sentence, I went to UICCS 582 and learn, right? So you can make you want your networks to kind of learn different types of syntax in this sentence, right? So one way is potentially you want some of your network to learn like attending to these entities. So you know like these are the entities that are relative to me, and there might be some relationship between these entities that have some meaning. And the other set of weight can be just focusing on the verbs, like I went and I learned, right? So if you don't use two separate hats and just like put them all together, you will have like really high weights in all positions, and well, it's not really effectively in telling apart these two different patterns, right? But if you separate them out, you can have two sets of different attention mechanism to focusing on different syntax. And so if we look at this matrix multiplication view of our attention, right, it's really kind of a gigantic matrix multiplication between these embeddings and the query matrix and key matrix. And the softmax is also like can be computed as like a gigantic matrix multiplication, right? So luckily, when you break everything down into separate sets of query and keys, we still have this nice property of like using it kind of as a gigantic multiplication. So effectively, we can imagine you breaking your key query value matrices into like number of heads parts. So right, so you just have the d divided by h, which is number of the attention heads. So you just effectively kind of shrink your weight matrices for key query values, but you have like multiple set of them. And when you compute these operations together, the only difference is when you apply the softmax, you only apply softmax within each set of attention weights you assign to. So like you can see that the multiplication is really not very different. You still use this gigantic multiplication in one step, and that gives you all the output that you need. The only change is happening in the softmax, where you only care about each set. You only compare softmax with each set of the key query. No questions so far? Cool. Okay, so now we have the some additional change to the architectures. We can talk about the training, right? Like we talked about this many times before. We don't want a single layer. We want a deep layer, and how we can get there. And like the trick is really similar across like convolutional neural networks and attention. Is basically come up with more efficient and more regularized, like intermediate layers, such that we do backpropagation. We don't have, we still have, but we have a limited impact from vanishing or exploding gradient. And then there's also like kind of the, so there's three tricks used here. Residual connections, we talk about it, and layer normalization is slightly different from the batch normalization we talked about previously. And one interesting trick is called scale dot product. So if we look at the vanilla dot product, right, when this dimension increase, your dot product will also be increase linearly with the dimension, and this can give you kind of exploding activations if you scale up your architectures. So and we don't necessarily need that, right? So and also we don't want that to become like a certain inductive bias of your model, right? If you have a longer sequence, you just have like more. If you have higher dimensionality, you have a bigger attention. So and that inductive bias is not necessarily useful. So we kind of want to control the performance between different models with different hidden dimensions. And the simple trick we can play here is just kind of divide our attention with the dimensionality. And this will basically regularize the scale of the attention regardless of how many dimensions you use in your hidden space. And this becomes the scale dot product, which gives us, which like automatically compute all of these, dot product and the scaling and the softmax on top of that. And this operator has been drastically accelerated inside, GPUs like CUDA kernels, and so I believe there's like super efficient operators if we do exactly this operation in the dot product. All right, so another trick that we talked about it a few lectures back is, of course, adding this residual blocks. And it's not anything that's different from convolutional neural network. It's just instead of bypassing a convolutional neural network, we're now bypassing a attention neural network. And the gradients, we get this like similar effect of kind of having the gradient flow back more efficiently, and so minimize the kind of the chance of getting vanishing gradients. And finally, they also apply this layer normalization, which is kind of also another trick similar to batch normalization, but instead of like normalizing within the batch, we normalize it within the dimensions of the hidden vectors. So effectively, if you have a embedding that has d dimension, we try to compute the mean and the variance across that d dimension, and we just normalize our features with respect to these two sets of transformation. And as I mentioned before, because we lose some degree of freedom if we do this. If we only do this operation, we kind of want to add it back by doing another two set of scale and bias parameters, and we make them learnable. Just by making these two parameters learnable, and we're able to like train it end to end. So this is, interestingly, this layer normalization works really well for attention architectures, and the batch normalization we talked about previously works really well for residual neural networks. And of course, like kind of these different types of regularization and inductive bias, plays well with different types of architecture, interestingly. So now connecting all of these together, we now have this transformer decoder, and basically the decoder is set up in a way that you go through all of this layer, and at the end you get this gigantic softmax to over all tokens that computes kind of the probability over tokens for your next token prediction. And in the encoder of transformer is not very different. I think the only change probably is just that instead of doing this causal mask, we no longer need it because we believe that all the information in the encoder is known at the time we decode. So we kind of remove this causality, and we want to make it like global to be able to look at the global context. And the simple trick is remove that mask, and that becomes the kind of the encoder architecture. And we can also remove, we can also add mask back to a single token of our entire sequence, right? And that will become the mask language model, where effectively we query the network with a question like, if I remove one of the token in the middle of your sequence, can you recover it given the context around it or given the entire sequence? So it's kind of learning kind of how well the model is able to coherently capture the independence between different context positions in the sequence. So transformer, and especially attentions, not just transformers, it actually solves all of these problems we mentioned in the beginning of the lectures, right? It's able to really learn these long-range dependencies without linear gaps, and we have less chance of getting vanishing gradient because we can directly connecting the tokens with different time steps in the encoding. And hopefully it will require fewer training steps and fewer computation time, and thanks to the parallelization capability to do parallelization. But as we mentioned, like when we talk about state space models, right, there is still some downside of transformer, which is the complexity of this attention computation, which is kind of square of n, where n is the number of tokens in your sequence. And this is especially painful in the training stage, because in the training stage you have like so much to compute. This is especially painful in the inference stage, because for every single token you add, you need to look at all of the previous tokens, and that can be kind of not ideal. I mean, I think the training stage is fine because of all of these parallelization. Okay, so there are. So given these constraints or limitations, there are definitely efforts that put into making this quadratic computation more effective. Perhaps like, what if we can make this cost down to linear? Like to the O of n, that would be very, very ideal, right? So I think there are a lot of like in the past 4 years, 3 to 4 years, there are a lot of work that try to make it more efficient. Most of them are just try to kind of do approximation of this quadratic attention, either like doing some low rank factorization, or even just try to make it like a linear operation that does not rely on like. So for here you can see that like the query side is not doing kind of you kind of chain them together, so one of it doesn't really need to be computed n times. Such that you kind of have a linear effect when we do this attention. So linformer is such example. And there's also a way to directly design attention mask, such that attention mask now becomes sparse. And particularly there's kind of this random dropping of attentions, and there's a window attention where if you believe like only the neighbors of each token matters, so we only need attention in this kind of short window along the diagonals. And there's also this global attention where like for each part, I just want to look at the every other tokens in the row or the column. And Big Bird is one of these sparse architectures that combine all of these together, and they kind of show that this approximately kind of give you some boost in terms of the sparsity of the attention without losing too much like capability of capturing the full attention matrix. I mean, but there's like a really interesting paper. I think it came out like 2 years ago or 1 year ago, I forgot. But they basically try to like systematically analyze all of these tricks or modifications that propose to transformer. And interestingly, like people find that a lot of the modification like are not very meaningful or effectively like not speeding up or like giving you a performance boost. But I think particularly this because our GPUs are hyper optimized for like the scaled out product. So once you inject sparsity into your attention, it actually does not save compute. It could give you additional compute when you try to compute the sparse attention, right? And then the sparsity is not really effectively used in some case. So, I mean, I think there are definitely certain types of attention that designed for a particular type of sparse attention, and there's also like flash transformers and butterfly transformers that from the architecture, the MLSys point of view, that try to speed up a lot of these things. But I think right now, what's being used, at least in the field, for example, in protein design, is still just like the vanilla transformer attention, like without too much modifications that's been introduced.
Would you say though, are they using the rotational positioning?
Yeah, the position encoding is something else. In terms of the attention mechanism itself, we're kind of pretty much almost using the vanilla ones. But this is not this. I mean, in terms of the speed up that we're getting, what I mean is we don't try to play with attention too much to get the speed up because that's not meaningful most of the time. But still, like I said, in for example AlphaFold, we do try to inject sparsity into attention because of our belief of like which positions you should be looking at when you do protein folding. Like if we believe that we shouldn't be looking too far away in the sequence, that will basically give us too much noise and unnecessary information, we still need to have this bias in our attention. But that's not for the purpose of accelerating anything. And again, like the rotary positional encoding is something like orthogonal to attention mechanism itself. I believe it's like the way of how we inject this relative positional encoding bias into the attention scores. So now we talk about kind of a lot of attention in NLPs. What does the attention look like in protein modeling, right? Especially for example, taking this evoformer from AlphaFold 2 as an example. So we talked about in the last lecture that in the protein folding task, or protein structure or function prediction task, a lot of time we can't just rely on a single sequence because there are like really few data in the database that give us this end-to-end training opportunity. So instead, we rely on the ensemble of sequence curated from this multiple sequence alignment process. So our inputs now becomes a set or a matrix of like n by L matrix, where n is the number of sequence in the multiple sequence alignment, and L is the length of the protein. Actually, in this evoformer of the AlphaFold, they actually introduced kind of a very interesting way of learning the attention by looking at basically the pairs of residues, and we explicitly have this pair representation that's learned for every pair of residues in the MSA, and we kind of give this information into a evoformer architecture that effectively try to model over this pair representation instead of just like a sequence information. And inside these evoformers, there are also like attention that's being used a lot. Now we can consider this attention being like a 3D attention, right? So instead of having a L by D matrix, we now have a L by L by D matrix, or here they say the R by R by C matrix. And our attention is applied on kind of this cube of the cube of these scalar numbers. And there are actually three special types of operators defined for this evoformer. The first is called like axial attention. So axial attention is introduced, I believe, in some of these attention for computer vision tasks, where you're also dealing with like a 2D pixels with an image. So they kind of wanted to design this special attention which look at every column and every row on this image instead of looking at every possible pairs. And this gives us a really good inductive bias for each pixel in this 2D space. So effectively, if you look at MSAs, they're also like these, right? So you have like number of MSAs and number of residues in the sequence, and you have this additional C, which is just the dimension of your feature. So you can still like apply a very simpler trick where you kind of across the MSA you have this row attention, which basically look at the interactions between each positions in the single sequence, and you have this column-wise attention, which is looking at the covariance across all different sequences at that position. And by doing these two steps sequentially, I believe it's the row-wise first, and then column-wise second. You kind of have the information propagate through like all pairs and also like all columns. And effectively, we can model kind of the covariance of different, across different positions. And then after these, after these axial attention, they do this outer product mean, which basically transform this R by C matrix into R by R by C. So you basically do the pairwise multiplication together and kind of explode the matrix from R to R by R. And then they further apply these sets of, what we can say like geometry-aware operators. Particularly, it can be breaking down as two steps of triangle update and two steps of triangular attention. So effectively, what it's trying to capturing here, we briefly talked about last time, is basically for every 3 points in this adjacency matrix, you can consider like every point of these adjacency matrix representing an edge, right, in your graph. So if you know that the 3 edges forms a triangle, this triangle must fulfill this triangle inequality where like the length of the two edge needs to be, like, when you sum them together, it needs to be larger than the third edge. So if you have like a pair representation like this, right, if you have 7 here and 3 here and 2 here, it doesn't fulfill this inequality, so this is really a bad representation because it breaks this inequality. So this triangular update and triangular attention is kind of designed to downweight the yield post cases where you break this triangle inequality. Particularly in the triangular update stage, it can be defined for both outgoing and incoming. What it does is basically for every edge, I and j, you kind of update the I and j with the multiplicative embedding from all the two edges in the triangle, the two other edges in the triangle. So you kind of consider like for every row, this is actually kind of a special way of doing like row and column attention, where you kind of at each row, you actually looking at all pairs of ik and jk, and you multiply them, and then you use that, you multiply these 2 pairs together to get the final update that will be included into the I and j. And you can also do it for the incoming edge, where basically you find, for example, instead of an upper triangular region, you use the lower triangular region to do this opposite update. So yeah, just 2 things to remember here. Like, this update is not symmetric, right? Because of this asymmetry in this computation, and it effectively captures, like, let the edge be aware of the other 2 edges. So we could consider this step of like they try to compute the distances between all 3 pairs. All 3 edges. And then the more interesting is this self-attention, where it's basically for each edge embeddings or each embedding in this R by R matrices, we also try to do attention across all different edges for that same node. And when we do this attention with different edge, the originate from the same node or like pointing at the same node, we let it aware of the third edge that is connecting these 2 edges together, right? So what effectively it does is it compute the normal attention across all pairs of edges for this same node, and then you just add additional bias from this kind of inferred third edge to this pairwise attention, and that gives you kind of a bias about what the constraints should be. So particularly, like, the first step is to compute normal attention, right, for each of these edge coming out of the same node I, and then you just do kind of this key and query multiplication, and you can get